Yes, welcome you all for the today classes. So in this today classes, we are going to solve some numericals on the Bernoulli equations. Okay, before going to solve the numericals, we should know the what is the Bernoulli equations and what are the terms which are included. Okay, based on this theorem, we are going to solve some numericals. Okay, so here already in the previous class, we discussed about the Bernoulli's theorem and Euler's equations. Okay, so we also derived these equations here. So what is the equation of Bernoulli's here? Bernoulli's equation for study incompressible flow of an ideal fluid. It is for the ideal fluid. So what is that? P by rho g plus v square by 2g plus z is equal to constant. So this here P by rho g is nothing but the pressure head, v square by 2g is nothing but the kinetic head, and z is the potential head, which is equal to constant. This is the Bernoulli's equation. It is for the steady and incompressible flow of an ideal fluid. Okay, so which term it includes? This equations we are having the pressure head, kinetic head, potential head, which is equal to constant. The sum of all these three head equal to constant. Okay, so we will take one by one here. The pressure head is equal to pressure energy divided by weight, that is given by P by rho g. That is what here it is there, P by rho g. That is the pressure head. Pressure energy divided by weight. So kinetic head is nothing but kinetic energy divided by weight. So that is here V square by 2g. This is the kinetic energy divided by weight, that is equal to V square by 2g. Next, third one is the potential head. That is equal to what? Potential energy divided by weight, which is denoted by the Z. The sum of all these three head is equal to constant. Okay, so now what is the Bernoulli's theorem here? In a steady continuous flow of a frictionless incompressible fluid, the sum of the, potential head, pressure head and the kinetic head remains constant at all the section. Okay, so this is the statement of the Bernoulli's theorem here. Steady continuous flow of frictionless incompressible fluid, the sum of potential head, the pressure head and the kinetic head remains constant at all the sections. This is the Bernoulli's equation, that is sum of pressure head, kinetic head and potential, which is equal to constant for all the section. Okay, so now the Bernoulli's equation between any two sections, we have to consider any two section. So here it is a section 1 and this is the section 2. So here at the entry of this section 1 we are going to use some parameters, that is P1, A1 and V1. So here P is nothing but pressure, area and velocity. So P1 is nothing but pressure at section 1, A1 is nothing but pressure area at section 1, V1 is nothing but velocity at section 1. So similarly pressure, area and velocity at section 2, and this is the Z1. We can say that Z1 is the potential head and it measures the distance between the datum to the section center. Here section center is here, section 1 center is here, that is representing Z1 but to the datum line. So Z2 is at the section head, center, the 2 section center is here, that is represented with the Z2. Okay, so this is about the this is how we can applying that Bernoulli's equation to this particular two sections. So according to the Bernoulli's theorem, we have to write the equation for the section 1 as well as the section 2. Okay, so what is the equation here? P by rho g plus v square by 2g plus z is equal to constant. So the same equations we are going to apply to this sections 1, then it becomes p1 by rho g plus p1 by 2z plus z1 is equal to, which is equal to what? P2 by rho g plus v2 square by 2z plus z2. That means here in the statement he has given the sum of potential head. This is the potential head. This is this is potential head, pressure head, kinetic energy. Kinetic head remains constant at all the section. That is whatever the pressure head, kinetic head and potential head at section 1, which should be equal to pressure head, kinetic head and potential at section 2. That's why P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus Vt square by 2g plus Z2. This is what how we are going to apply that Bernoulli's equation for the two sections, section 11 and section 22. Okay, so to solve the numericals for the ideal fluid, this equation is for the ideal fluid, we have to remember the equation. So this equations and the terms which are involved in this equation, that is pressure, kinetic and potential head, that we have to remember to solve the numericals. Okay, so now the Bernoulli's equation for the real fluids. Bernoulli's equation for the real fluids. This is for the ideal fluids. So already we know the what is the ideal fluid and a real fluid. Okay. So this is the real fluid. This we have to. This equation is for the real fluid. Nothing is there. So the same heads P1 by rho g plus V1 square by 2g plus z1 is equal to p2 by rho g plus vt square by 2g plus z2 plus another term is there, that is the loss, HL, that is we call HL is the loss of energy head between the two sections. Okay, so in the real fluid what happens, there is a losses of head energy while flowing from section 11 to the section 22. That fluid is having the some losses, that losses if you are considering, that is the real fluid. So in the most of the cases all we are going to consider the real fluids only. Okay, and this is for the ideal fluid. That ideal fluid is nothing but it is not having any viscosity, and this is real fluid it is having some viscosity. Due to that viscosity, the resistance of flow of resistance is occurs, that is here he has given. In a steady flow of fluid with the energy loss, the total head at any section is equal to that at a subsequent section plus loss of head occurring between the two sections, that is the loss of head. This is so the same Bernoulli's equation theorem plus we were having one extra term, that is the loss of head in the real fluids. It is for the real fluids. So all the liquids are more or less aqueous and therefore is accompanied by the friction forces or a resistance which uh, hinder the motion. Okay, so therefore the from the section 1 to section from section to section there must be expenditure of energy by the liquid in overcoming the resistance, that is the here this energy. Obviously the energy at downstream is lesser than the upstream section by amount equivalent to the friction loss. Okay, so we are going to apply the Bernoulli's equation for this section and this section. So the energy loss which is added to the section 2 to term. Okay, so you have to remembering these two formula. One formula is for the real food and another one is for the ideal food to solve some numericals. Now let's start the numericals on the Bernoulli's equations. Okay, so first problem he has given, the figure shows the pipe of varying diameter conveying the water from section 11 to the section 22. The diameter at these sections are respectively 300 mm and 600 mm. The pressure at section 11 being 6.75 meter of water column. Find the pressure head at section 22 if the rate of flow in the pipe is 0.360 meter cube per second. So this is the statement of the problem he has given, and also along with this statement he has already given the figure. He said that the figure shows. So here there is one varying diameter pipe is there. Inside that pipe the water is flowing. The water is flowing from the section 11 to the section 22. So and also we know the diameter at section 11 and diameter at section 22. Okay, here uh, he has given that pressure head. Okay, that is 6.75 meter of water column. Okay, and also he has given the flow rate here. Okay, so and also he has given in the figure itself 3 meter and 7.5 meter that is the datum potential head from the datum line, potential from the datum line, 3 meter and 7.5 meter of water. So in the figure itself he has given these two terms are not given in the statement of the problem. In the figure he has given that potential head from the data line is 3 meter at section 11 and 7.5 meter at section 22. Okay, so first we have to write the given data. Flow rate he has given that q is equal to 0.36 meter cube per second. Directly he has given in terms of meter cube per second, no need to change this unit. Okay, and also he has given the inlet diameter at section 11, so that is d1 he has given 300 meter, 300 mm, so that we have to convert it into meter, that is equal to 0.3 meter. Outlet diameter at section 22 he has given, that is d2 here 600 mm, that is in terms of meter that becomes 0.6 meter. Okay, so pressure at section 11, so already he has given the pressure at section 11, so that is the, so in the Bernoulli equation we know the pressure head is nothing but P1 by rho g, so that we have to write here P1 by rho g is equal to 6.75 meter of water. Directly he has given in terms of meter of water, then no need of conversion here. Next, he has in the problem in the figure he has given the potential at section 11, that you have to consider Z1, which is equal to 3 meter of water, and potential head at section 22 Z2 is equal to 7.5 meter of water. So this is what he has given in the problem statement of the problem. Now we have to solve this problem. Okay, so what we have to find out here, that is important. First we should know what is the parameter he has given and what parameter we need to find out here. So first find the pressure head at section 22, so that is at section 22 we don't know the pressure head, that we have to find out here. So in the section 11 he has given the pressure, but to section 22 we have to find out here. Okay, first write down the Bernoulli's equation for flow between the section 11 and section 22. So already we know the equations for the if he has not given any energy losses, that is the HL value, then you have to consider it for the ideal fluid. So for ideal fluid we are having the Bernoulli's equations here, P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. This is the Bernoulli's equations. Okay, so in this what are the parameter he has given, that we have to find out here. He has given that P1 by rho g directly he in the given statement, uh, and we don't know the V1 values, V1 by 2g plus Z1 he has given this parameter pressure head at section 22 we have to find out, and we don't know the V2 also, V2 by rho 2g, and we know the Z2. Then in these equations we are having the two unknowns, that is velocity and the pressure head. So we have to find out this velocity by using the continuity equations here. Q is equal to A1 V1 is equal to A2 V2. This equation is called as the continuity equation. So first velocity at 1 1, velocity at 1 1, that V1 is equal to Q by A1. The Q is equal to A1, V1 is there. We need to find out the V1 here, that is V1 is equal to Q by A1, and A1 is equal to 5 by 4 D1 square. So already we know the diameter. So from this equation we will get the area, so that we have to substitute here. V1 is equal to 0.360 by A1, that is given by 5.093 meter per second, 5.093 meter per second. Okay, so next we have to find out the V2, that is Q by A2. A2 already A2 we can find out it by 5 by 4 D2 square, that is 5 by 4 into D2 is nothing but 0.6 square. So from this equation so we will get that V2 is equal to Q will already he has given, that is 0.360 divided by A2, which is equal to 1.273 meter per second. So we get that V1 and V2 value. So in this equation the only unknown thing is that P2 by rho g. So V1 we get, V2 we get, Z1 and Z2 he has given, and P1 by rho g he has given. Just we have to substitute here all the values except this P2 by rho g. So that is our pressure head at section 22. Okay, so substitute these values and calculate, we will get that pressure head at section 22 is given by P2 by rho g is equal to 3.489 meter of water. This is our required answer for this uh, problem. Okay, so this is the first problems. Okay, first what we have to do, first write down the given datas, next write down the Bernoulli equations, just just check the value which are given in this formula. So unknown things that v1 and v2 can be calculated by using these continuity equations. So in this area, and a1 and a2 can be calculated by using this d1 and d2, and those value we have to substitute to get the v1 and v2. So already after getting these two value, we have to substitute in this equation, so we will get that our required answer, that p2 by rho g is equal to 3.489 meter of water. This is our first problem. Okay, so next so in the second problem, water flows at the rate of 75 liter per second. So in a pipe whose diameter at section 11 and section 22 are 300 mm and 150 mm respectively, which are at height 5 meter and 3 meter above the datum. If the pressure head at section 11 is 450 kilopascal, find the pressure at section 22 neglecting loss of energy. Okay, so here he has given one pipe that is varying cross section. So at section 1 it is having the diameter 300 mm, and section 2 it is having the diameter 150 mm, and also he has given the datum height, that is 5 meter and 3 meter uh, here, and also he has given pressure at section 11 in terms of what, kilopascal, 450 kilopascal. So similarly, previous one, we have to find out the pressure of pressure at section 2 too. Okay, neglecting the loss of energy, that means it is also a ideal fluid. Okay, so write down all the given data. First, flow rate is he has given 75 liter per second. So here in terms of what he has given, liter per second, that we have to convert it into meter cube per second, that is q is equal to 75 into 10 raised to minus 3 meter cube per second, that is. And also he has given that d1 and d2 300 mm, which is equal to 0.3 meter, and d2 is 150 mm, which is equal to 0.15 meter. Okay, that we have to convert it into meter. Okay, pressure potential head section 11, z1 is equal to 5 meter of water, potential head at 2 z2 is equal to 3 meter of water. Pressure head at section 11, p1 is equal to 450 kilopascal. He has given the in this problem he has given the pressure at a kilopascal, that we have to convert it into pascal, that is multiplied with the 10 raised to 10 raised to 3. Okay, so here so 10 raised to 3 pascal. Okay, now write on the Bernoulli equation for the flow between section 11 and 22. So that P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Okay, so that again we don't know the V1 and V2 in this problem also, so that we have to convert it calculate it by using this continuity equation, that q is equal to a1, v1 is equal to a2, v2. Velocity at 1 is equal to v1, which is equal to q by a1, and and a1 is equal to 5 by 4 d1 square. So diameter here is given. So from this we will get the a1 value. Substitute q and a1, we will get the v1. Okay. Similarly, velocity at section 2 too. V2 is equal to q by a2, and again a2 is equal to 5 by 4 d2 square. So from this we will get the values. We will so substitute here in this equation, we will get the v2. Okay, so now density of water, already we know that rho is equal to 1000 kg per meter cube, 1000 kg per meter cube, because he has given that in terms of pascal we have to consider here the density also. Okay, and substitute all the equations here. The pressure he has given, that is 450 into 10 raised to 3 divided by 1000 into g value is 9.81, 9.81, that is p1 by rho g. Rho is 1000 into g is 9.81, okay, into 10 raised to 3 plus v1 v1 is 1.061 meter per second, that is v1 square is that we have to substitute all the values. Okay, z1 is 5 here. Okay, and p1 p2 by rho g we don't know, we need to find out that parameter only. And the next v2 square, v2 is 4.244 meter per second, so substitute here. And 2 into g is 9.81 plus z2 is 3. So substituting all the values and calculate, we will get that p2 by rho g is equal to what, 47.01 meter of water. So we'll get that in terms of what, meter of water, that we have to convert it into pascals. Okay, so that is how to convert that. P2 is equal to 47.01 into rho g, into rho g. So we have to take this term to this side, then it becomes pascal. Okay, that is 47.01 into 1000 into 9.81, that we will get P2 is equal to 461.18 into 10 raised to 3 pascal. Okay, so this is our required answer. Okay, so with this we will complete today classes. So in the next class we will solve some more problems on the Bernoulli equations. Okay, thank you.